Welcome to Copilot Podcasts, an algorithm that deliberately ignores capacity on its very first step. And that's not a bug, that's the whole point. Today, we're breaking down the Capacity Facility Assignment algorithm, specifically how it builds an initial solution from scratch, why it sweeps an entire grid instead of chasing a gradient, and how two completely distinct families of optimization phases clean up what that first step leaves behind. By the end of this episode, you'll understand why the design choices here are sharper than they look, and you'll be able to follow the logic of every phase from construction all the way through to the final refinement search. I've got someone here who's been deep in this document, and I want to start with what I think is the most counterintuitive thing in the whole spec. So, walk me through it. Why would you ever build a solution that ignores capacity on purpose?
So the main construction algorithm, it's called build base result in the spec, is a pure, greedy, nearest facility assignment. For every customer, it just picks whichever facility is geographically closest. That's it. No capacity check, no awareness of how loaded any facility already is.
And that's intentional.
Completely intentional. The document is explicit about this. It says the algorithm is, quote, trivially optimal for the distance objective in isolation, and whether it happens to also respect capacity is entirely a property of the data, not something this step tries to guarantee. So you're getting the best possible starting point for distance, and then everything that comes after is about repairing the capacity damage that creates. It's kind of like picking a checkout line at the grocery store, right? You go for the shortest one, you don't think about the person at the front who's about to pay with a check and dispute three prices. You optimize for what you can see immediately.
That's actually a really good analogy. You're greedy in the moment, and then you deal with the consequences. And the spec is very clear that this is a feature, not a flaw. You want the cheapest possible construction so that the optimization phases that follow have a clean, well-defined starting point to work from.
Okay, so you've got this initial labeling, every customer assigned to their nearest facility. Then what? How does the algorithm actually know how good or bad that assignment is?
That's where the score algorithm comes in. It evaluates the labeling against three separate objectives simultaneously. First, mean distance, the average travel distance across all customers. Second, total overflow ratio, how much the facilities are over their capacity limits. And third, utilization variance, how evenly the load is spread across facilities.
So it's not just one number you're optimizing, it's three things at once.
Right, and the spec combines them into a single comparable metric using a penalty weight, lambda, that scalarizes the overflow and variance terms. So you get one number you can rank rows by, but that number is encoding all three objectives. And here's the thing, the algorithm doesn't just run this once, it sweeps across a three-dimensional grid.
Wait, a three-dimensional grid? What are the three dimensions?
K, which is how many facilities are active, lambda, the penalty weight, and theta, a rotation angle applied to the facility positions before reassignment. The algorithm, called run in the spec, sweeps every combination of those three parameters and produces one scored row per combination. That's your candidate pool.
And the rotation angle thing is interesting to me. Why are you rotating facility positions? That seems like a strange thing to do.
So the rotation is a way of exploring different assignment landscapes without changing where the facilities actually are. You rotate the facility positions by some angle, reassign customers to the nearest rotated slot, and then snap each slot back to its nearest real facility. It's a geometric trick that lets you discover assignment patterns you'd never find by just running the greedy construction once.
Okay, and the spec is very deliberate about how the loop is structured, right? There's something about hoisting the expensive work.
Yeah, this is a nice engineering detail. The expensive geometric work, building the base result, doing the rotation and reassignment, happens only as often as it has to. Score, which is the cheap step that just reads the already fixed labeling, runs as the innermost loop. So you're not redoing geometry every time you change lambda, you fix the labeling, then sweep lambda cheaply across it.
Smart. So now you've got this whole grid of candidate rows. And the natural question is, why sweep the whole grid? Why not just start somewhere and follow the gradient toward a better solution? That's what gradient descent would do.
And this is where the document gets really interesting because it actually runs the experiment. The spec tests this on a benchmark dataset, 300 points, 5 irregularly placed blobs. And when you sweep the rotation angle at 1 degree resolution, the comparable score as a function of angle is genuinely multimodal. Not one smooth hill, 19 distinct local peaks, and 52 if you count every single degree boundary blip.
19 local peaks. So gradient descent is going to get stuck.
Exactly. And the spec proves it. They run hill climbing, the discrete analog of gradient descent, from 24 evenly spaced starting angles every 15 degrees. Only one of those 24 runs reached the true global maximum. The other 23 converged to local peaks, landing anywhere from 82.79 to 10604, short of the optimum by amounts ranging from 8 to 31 points, with no signal available from a single run to tell you which case you're in.
So 23 out of 24 times, you think you're done, but you're not.
And you have no way of knowing. That's the really painful part. The hill climbing result looks like a valid answer. It converged. It's locally optimal, but it's nowhere near the global optimum, and the algorithm has no mechanism to detect that.
It's like hiking in thick fog where you can only feel the ground right under your feet. You walk uphill, you reach a peak, you think you've summited, but there's a whole mountain range just beyond the fog you never even considered.
That's exactly the failure mode, and the exhaustive sweep sidesteps it entirely. The spec shows the application's actual sweep, using a 6-degree step, which is the default, lands within 2.25 of the true 1-degree optimum, deterministically, regardless of where the sweep begins. Because it checks the whole domain, there's no starting point to get lucky or unlucky about.
And then the batch run goes even further, right? It doesn't just fix K at 5 and sweep the angle.
Right, and this is the result that really drives the point home. The batch run sweeps K from 2 to 20, the proximity threshold from 0.05 to 3, and theta across the full 360 degrees, that's 411,540 combinations, and it finds a score of 122.531 at K equals 7, and theta equals 106 degrees. That's not just a closer approximation of the K equals 5 optimum, it surpasses it entirely, at a configuration that hill climbing and the single angle run never even considered.
Because they were holding K fixed at 5 the whole time.
Exactly. And the spec makes a really sharp point about why K and the proximity threshold have no gradient descent analog at all. Hill climbing works on the angle axis because 206 degrees and 205 degrees describe very similar rotations. You'd expect their scores to be close, so following the better neighbor is at least a reasonable strategy, even if it gets trapped. But K equals 7 is not a small perturbation of K equals 5. It's a completely different number of clusters, and the construction algorithm produces an entirely different labeling from scratch. There's no gradient to follow.
So for those axes, exhaustive enumeration isn't just the safer choice, it's the only choice that makes sense.
That's the spec's exact conclusion. And it's worth sitting with that for a second, because it's not just a performance argument, it's a structural argument. Gradient descent's one advantage, cheapness, comes from exploiting a neighbor structure that only the angle axis actually has. For K and proximity, it has nothing to exploit and no path forward.
Okay, so you've got your grid of candidate rows. Now what? This is where the two phase families come in.
Right. And the two-family split is, I think, the most elegant design decision in the whole document. Every phase after run is optional, and each one belongs to exactly one of two families, distinguished by one question. Is this phase allowed to make the distance objective worse in order to relieve capacity overflow?
And the answer is either yes or no, with no middle ground.
No middle ground. Capacity enhancement phases, yes, they can worsen distance to fix overflow. Distance squeeze phases, no, they are structurally constructed so they cannot worsen overflow. It's not a policy, it's a guarantee baked into the acceptance condition of every algorithm in that family.
Let's go through the capacity enhancement family first. What's in there?
Two phases. The first is rebalance, which shows up in the UI as get optimal. It's the conservative member of the family. It only ever moves a customer into already free capacity, no evictions, no forcing anyone out. It always prefers the nearest facility with room, so it repairs overflow while doing the least possible damage to distance for each individual move. The spec calls it a best effort repair, not a guarantee of zero overflow.
So it might not fully solve the overflow problem.
It might not if no facility anywhere has room. That's where force balance comes in. It runs rebalance first, and then for whatever overflow is still left, it's willing to evict an already well-placed customer, someone with a low distance assignment, and move them elsewhere to open room. The spec says this is the phase that most directly embodies the family's defining trade. It accepts a worse mean distance specifically to buy a better total overflow ratio.
You're robbing Peter to pay Paul, essentially. You're making one customer's assignment worse to fix the facility's capacity problem.
That's exactly it. And the spec is very clear that you should never run both get optimal and force balance blindly. You pick one based on what matters more in your situation, distance conservatism or closing overflow.
Okay, so once you've handled the capacity side, you move into the distance squeeze family. And this is where the structural guarantee becomes really important.
Right. Every phase in the distance squeeze family shares one structural guarantee. A candidate change is applied only if it does not push any facility's occupied load past its capacity. That single check, repeated in every algorithm in the family, is what makes them Pareto safe with respect to overflow. They can only match or improve total overflow ratio, never worsen it, by construction.
And there are 4 phases in this family?
4, yes. The first is move improve, labeled move in the UI. It's the cheapest squeeze. Relocate one customer at a time into a facility that is already strictly closer and already has enough free capacity to take them. No eviction, no trade, just a direct move if the conditions are met.
And the limitation there is obvious. If every facility is exactly at capacity, there's nowhere to move anyone.
Exactly, and the spec acknowledges this directly. That's why Swap Improve exists. Instead of moving one customer, it trades pairs of customers between two facilities. A trade needs no free capacity at all, you just need both facilities to stay within capacity after the exchange. So you can make progress even when every facility is full.
That's clever. You're not adding load anywhere, you're just redistributing it.
And then Aggressive Swap generalizes that further, from pairs to whole groups. Every customer at Facility A who would rather be at Facility B traded against every customer at B who would rather be at A. Only the two group totals need to balance within capacity. So it closes cases where no single pair matches but a combination does.
So you're escalating in power and cost as you go through the family.
That's the recommended execution order from the spec. Try Move first, it's the cheapest by a wide margin. Escalate to Swap Improve, then Aggressive Swap, only if Move plateaus. Each is more powerful and more expensive than the last, so paying for them is only justified once the cheaper option has genuinely run out of room to help.
And then there's Refine, which sounds architecturally different from the other three.
Very different. The spec calls it a ruin and recreate step wrapped in its own two-axis local search. The underlying mechanism is evict and reinsert. It evicts a fraction of customers from their current facilities and reinserts them greedily into the best available slots. And then Refine wraps that in a search across both rotation angle and eviction percentage.
So it's not just tweaking the current assignment, it's partially destroying it and rebuilding.
Right. And there's an important nuance here about what Refine actually depends on. The spec is explicit that Refine does not require get optimal or any other phase to have run first. Two independent facts make this true. First, the best of the best list it draws candidate rows from includes raw run output plus every optimized collection, so a row straight off run is a legitimate candidate. And second, Algorithm 10 itself rebuilds its labeling from build-based result at every angle it tries and always applies its own rebalance pass before evict and reinsert. Whatever phase history the input row carried is discarded and recomputed fresh.
So running get optimal first doesn't change what Refine does, it only changes which row got selected into the best of the best list.
Exactly. And the acceptance condition for Refine is worth spelling out, because the spec makes it explicit as code for the first time in the document. Overflow is a threshold the candidate must not cross past the current best. Distance is the objective that must strictly improve for the candidate to replace it. That's the family's defining contract, written down explicitly.
So the two families are really two different philosophies about what you're willing to trade. Capacity enhancement says, I will sacrifice distance to fix overflow. Distance squeeze says, I will never touch overflow, I will only make distance better.
And the spec's conclusion puts it really cleanly. It says the two-family split is not a cosmetic grouping, it is the same accept-reject discipline, applied consistently. Capacity enhancement phases are judged by whether they relieve overflow and are explicitly permitted to spend distance to do it. Distance squeeze phases are judged by whether they reduce distance and are constructed so they structurally cannot spend capacity to do it. And every phase in the document, including the elaborate ruin and recreate search behind Refine, reduces to that one rule once you write down its acceptance condition. That's the spec's exact point. Table 6 in the document makes this visible at a glance. Every phase, its family, what condition it accepts a change under, and its computational complexity. It's a really clean summary of the whole system.
Let's talk about the complexity for a second, because I think that's where the recommended execution order really makes sense. Move is O of P times N times K. Swap Improve is O of P times N squared. Aggressive Swap is O of P times K squared times N log N. Those are very different cost profiles.
And that's exactly why you don't just run Aggressive Swap first. The spec is very deliberate about this. You escalate only when the cheaper option has genuinely plateaued. There's no benefit to paying for Aggressive Swap's cost if Move still has room to improve the solution.
And Refine is listed last, not because it structurally depends on the other phases, but because it's the most exploratory and most expensive tool in the family.
Right. It's restricted to the already reduced best of the best list rather than the full raw grid, specifically because of cost. You let the cheaper phases reduce the field first, and then Refine does its ruin and recreate search on the survivors.
I want to go back to something you said earlier about the adaptive circle intersection method, because I think it connects to something interesting about how the centroid placement works differently from k-amines. Yeah, this is a detail the spec dwells on. K-amines always sets a centroid to the arithmetic mean of whichever points are currently assigned to it. It's a fixed rule, blind to whether that mean actually sits anywhere near where the assigned points are dense. Adaptive circle intersections candidate centroids come from a completely different source, perpendicular bisector intersections of a circle through each point and its nearest neighbor. It's a purely local geometric construction tied to the data's own point-to-point spacing.
So k-means is computing a global average, and adaptive circle intersection is tracking local density structure directly.
And the proximity threshold is literally the knob that decides how finely or coarsely the resulting centroids track the dataset's actual density shape. Small values keep many candidates positioned tightly around local density peaks. Large values merge nearby candidates into fewer, coarser positions. K-means has no equivalent parameter. You can't make it more or less locally adaptive because its centroid rule never changes. And that's why the batch run at k=7 found a score of 122.531 that surpassed the k=5 true maximum entirely. It wasn't just finding a better angle, it was finding a better configuration space altogether.
Exactly. And the spec is careful to note that the k=5 maximum of 114.0119 was always the best achievable at k=5. It was never claimed to be the best achievable overall. The batch run's 122.531 is direct measured proof that a richer search finds a still better configuration, not just a more reliable path to the same one.
That's a really important distinction. You're not just getting a more reliable answer to the same question, you're asking a better question.
And that's the whole argument for exhaustive grid search over gradient descent in one sentence. Gradient descent can only answer the question it was given, from the starting point it was given. The grid search asks every question simultaneously and reports the best answer it found.
So when you step back from everything we've covered here, the greedy construction, the grid sweep, the two-phase families, what's the through line? What's the design philosophy that connects all of it?
I think the through line is clarity about what each component is responsible for. Build-based result is responsible for one thing, the best possible distance assignment, full stop. It doesn't try to handle capacity. The grid sweep is responsible for one thing, exploring the configuration space exhaustively, because the landscape is multimodal and gradient descent will get trapped. And then the two-phase families each have one clearly defined job, with a structural guarantee that they can't accidentally do the other family's job.
There's no phase that's trying to do everything at once.
None. And I think that's what makes the system trustworthy. You can look at any phase and know exactly what it's allowed to do and what it's not. The acceptance condition is the contract, and every phase honors it.
Here's what I find genuinely surprising about this whole system. The algorithm that starts by completely ignoring capacity ends up producing a system with the most rigorous capacity discipline of any component in it. The construction is capacity blind, and then every single optimization phase is defined by its relationship to capacity. That's a full circle design.
And it's not accidental. The spec is very deliberate that the construction's capacity blindness is what makes it cheap and what makes it the right starting point. If you tried to build capacity awareness into the construction, you'd be doing more work up front for a solution that the optimization phases are going to reshape anyway. You start simple, you score honestly, and then you fix what needs fixing with the right tool for the job.
And the right tool for the job depends entirely on whether you're in a capacity problem or a distance problem.
That's the two-family split in one sentence. And the spec's recommended execution order follows directly from that. Fix capacity first with get optimal or force balance, then squeeze distance with move, swap improve, aggressive swap, and refine, in escalating order of cost and power. You never run a distance squeeze phase on a solution that still has overflow you haven't addressed, because you'd be optimizing the wrong thing.
So the execution order isn't arbitrary, it's a direct consequence of the phase family structure.
Completely. And I think that's the insight that makes this spec more than just a list of algorithms. It's a coherent argument for a particular way of thinking about multi-objective optimization. Separate your objectives, assign each phase a clear responsibility, and build the acceptance conditions so the phases can't accidentally undermine each other.
Here's what this really comes down to, and I think it's worth saying plainly. If you're building any system that routes things, customers to facilities, deliveries to warehouses, requests to servers, you face this exact tension between distance and capacity. And the lesson from this spec is that the answer isn't to find one algorithm that balances both. It's to be explicit about which problem you're solving at each step, and to build your acceptance conditions so that clarity is enforced structurally, not just by convention.
And the exhaustive sweep lesson applies beyond facility assignment too. Anytime your optimization landscape is multimodal, and most real-world landscapes are, gradient descent is going to get trapped somewhere that looks like a solution, but isn't. The question isn't whether to sweep exhaustively, it's whether you can afford to. And the spec shows that with smart loop hoisting and cheap inner steps, you can cover a lot of ground without paying for it every time. 411,540 combinations in the batch run, and the expensive geometric work only happens as often as it has to. That's the engineering discipline that makes the exhaustive approach practical. You don't just sweep everything naively, You think carefully about what's expensive, hoist it to the outer loop, and let the cheap step run as the innermost operation. The result is a search that's both thorough and efficient.
We started this episode with an algorithm that ignores capacity on purpose, and we're ending with a system where every single phase is defined by its relationship to capacity. That's the design insight worth carrying out of this conversation. The algorithm that starts blind ends up with the clearest vision of all. Thanks for being here, and thanks for listening to Copilot Podcasts.